Hello, welcome back to Organic Chemistry 2341. We're going to continue on with our chapter 2 here. But first, let me give a comment about our SI sessions. I apologize for all the difficulty we had last week with our SI sessions. We will be putting out a new list of in fact, I will email it right after this class, the new list of SI sessions that are available. And if you go onto the app, you'll see which ones that you can, where the links are to these things. I'm going to post the links to the Zoom links to all the meetings as soon as I get them from the SI office. Okay, so we had a little problem there. And so what we're going to do is we're actually going to have you split between two other SIs. And so the individual classes will be taught by the same SI through the rest of the semester. However, Marcus will not be our SI anymore. So as such, I hope anything you missed last week, you'll have an opportunity to make up. And so I apologize for that. It will not reflect badly on your grade. It's just going to make you need to go. I think anybody who tried to log in will get credit for stuff for last week. Okay. If not, there's always an opportunity to do a couple sessions in a week to get all the way back up to your 10 before the end of our calling time, which I believe is in April. So double check that on the Canvas site under the SI section of the syllabus. Okay, questions on SI? Okay, great. Now what we're going to do is we're going to move on with the second part of chapter 2. And since homework is due today, I thought it'd be very good to finish that lecture up today. And that is on IR spectroscopy. Now, the reason I like IR spectroscopy right here is we just learned all these different functional groups, right? And all these different functional groups, we need to have, like, I think, proof that they exist, right? So one way to prove that they exist is to actually analyze them by this method. IR spectroscopy, or infrared spectroscopy, is a very powerful tool that shows you the functional groups you have, and if you are actually converting from one functional group to the next, it demonstrates that in a very tangible way. Okay, so let me go ahead and share my screen with my slides. This is section 2.2 on the Canvas slides there, module 2.2 if you're on Canvas there. They're also, I believe, on Top Hat somewhere as well. Okay, and so that you can find them in either space. So I'm going to go ahead and blow this up a little bit. There we go, and start talking. So infrared spectroscopy. So we're going to use wavelengths of light to figure out that bonds exist. Okay, that's the cool part of this. And the whole reason this works is that all of the different kinds of lights that we can see and can't see all fall in what we call electromagnetic radiation, which means they have an electric wave component and they have a magnetic field component. And so when bonds react with either the magnetic field, which we'll do later in NMR, or with the electric field, we can get absorption of different energies by different types of bonds. And we get absorption of it where we are absorbing one energy and not absorbing the others. We can see which functional group is present. Okay, so that's the cool part of the IR spectroscopy. So let's look at the entire electromagnetic spectrum here. And as we see that the visible spectrum is just a tiny little wedge of the entire electromagnetic spectrum, we can go way over here on the right side of the screen right here. And these are radio waves. And so these are very very low frequency materials, very long wavelengths. This wavelength is in the order of 10 miles. You actually have one whole wave going between.
Dr. Irvin?
Yes.
Sorry, I don't see that you're on the next slide.
Okay, let me stop. Oh, my screen sharing has paused for some reason. I'm going to stop sharing and reshare. Okay. And
there you go.
Okay. I resized it and it freaked out. That's what happened. Okay. So did you see this slide here?
Now we can.
Okay, so this slide shows you that every part of every wave, every type of light will have an electronic component, which is orthogonal to the magnetic component. In this particular case with IR, we're going to look at that electronic wave, and we need to have an understanding of that. And we'll use that magnetic field when we do proton NMR in a later chapter. Okay. So the electromagnetic spectrum is really, really big. And we start with just this small little wedge that we actually see with our eyes, but we can use a bunch of different things. And if we look here, we have increasing wavelength increases from here. So that means these are very tiny waves right here. And if we look over here, but they're also very high frequency. So wavelength and frequency are inversely proportional because wavelength is the peak to peak distance. Frequency is how many vibrations per unit length. So as that peak to peak distance increases, the frequency also increases. Okay, I'm sorry, decreases. They're inversely proportional. So your little tiny waves, you have a high frequency. Big long waves, you have a very low frequency. Okay. So then as we move out of the radio waves here, we get into microwave, which is really useful. And we know that actually microwave interacts with bonds as well because it absorbs between the oxygen and the hydrogen, heating up our food. So microwave radiation also does that same thing, where it's absorbing energy and causing certain bonds to vibrate. We're going to be talking mostly about the IR today, but UV, X-rays, and gamma rays are much higher frequency, much higher energy wavelengths. Okay. So let's talk about that IR section there. So what we do when we have a sample is we actually create a burst of IR light that has all the frequencies available to it. And then we put it into a device which causes the light to split around. And what this does is this gives us an idea of the time regime that pulse of light came out. Then we shoot it through the sample. Now, when we shoot it through the sample, certain bonds will absorb certain energies of that light, and therefore they will be missing when we look at the spectra we obtained. Some of the frequencies of light are not going to be absorbed because there's nothing to absorb some energy, and we'll have what we call our baseline. So there's going to be a lot of some of the light transmitted, but some of the light is going to be removed, and that part that's removed is proof we have a certain bond there. Okay, so they're actually gotten really, really easy nowadays. You used to have to do a whole bunch of prep on it. Right now, all you have to do is, this is a little piece of diamond. You put a drop of your stuff on the diamond and hit go, and you're done. It's amazingly easy to do these things now. So, okay. So I said frequency is important in this. It'll tell us where which wavelengths we're looking for here. Now in IR, we typically use the unit of reciprocal centimeters, or centimeter to the -1, as our frequency. And we do that because of when they started making interferometers, the thing that that makes the light go back and forth, that just seemed to be the unit they wanted to use. And it made nice round numbers. In our IR range, we go from about 4,000 wave numbers, reciprocal centimeters, to about 400. So we had that great, differentiation that we have. Okay, now I said that the certain energies would be absorbed by different types of bonds. So why? Okay, so the idea here is we actually have that frequency is proportional to the energy absorbed. Okay, that wave number is proportional. And the reason we have it is that there is an effect of, number one, the type of bonds we have. The stronger the bond we have, the higher a frequency, or the higher the wave number we have. Think about that. If you have a very strong bond, it's going to be vibrating a much higher frequency than if you had a very weak bond. It's going to act like two rocks on a spring and go like that. And so as the rocks get heavier, they're going to be going faster and faster. The second thing that's affected is the mass of the atom. Because if you think about it here, you had a rock here and a feather here, and you put it on a spring, the feather is going to be doing all the motion, the rock's not going to move at all. And so that will also affect our frequency. So let's look at first the mass effect right here. And in the mass effect here, we have a carbon-hydrogen bond, and then we have a carbon-deuterium bond. So deuterium is an isotope of hydrogen, just one more proton, okay? And then we have a carbon-carbon bond, okay? And if we look at the frequency difference here, a carbon-carbon bond vibrates at 1200 wave numbers, okay? By decreasing the mass to that of a deuterium, it goes down to it goes up to 2100 wave numbers, okay? By the time we get to hydrogen, that's 3000 wave numbers. So that's a very high frequency for the set of things attached to carbon. And hydrogen is our lightest element, okay? That means that everything that has an element hydrogen bond is probably going to be a high frequency, okay? So that's the first thing to look for, is the element versus the hydrogen will give us a high frequency. And over here we look at it, we have comparing oxygen, nitrogen, and carbon, and notice they're all right around that 3000 wave number zone. All right, now let's look at the second component here, the larger F, or the stronger bond. Okay, so if we look at carbon-carbon bonds, we're not changing the mass. So there's that mass doesn't affect the system. It's only about the strength of the bond. So again, our carbon-carbon bond, a single bond, is right around 1200. By turning that into a double bond, they're bound tighter together, and we have a stronger bond, therefore the frequency goes up. And by the time we get to a triple bond, the frequency goes up again. Okay, so this is true for all of the elements, all of the different bonds. As you go from a single bond to a double bond to a triple bond, you increase the frequency. And in the case of nitrogen, we actually can get a triple bond with nitrogen. We can't do that with oxygen, so we can only compare the single bond and the double bond here. And notice there's a significant frequency shift. So mass affects the frequency. The light mass elements like hydrogen have the highest frequencies. Bond strength affects frequency. The stronger the bond, the higher the frequency. Okay, so do we understand why we have different frequencies associated with those different types of bonds? Okay, now what I'm going to do is I'm going to take this knowledge and kind of lay it out in a pattern to make it easy to recognize. Okay, so now there's a bunch of different types of vibrational modes. Well, so if you just had two atoms and you hit it with IR light and it starts absorbing that energy, it's going to do, this spring and ball thing where it just kind of vibrates back and forth, okay? And it takes a certain amount of energy to make it do that. However, there's additional vibrational modes available to us once you put a third atom on there. So in a third atom, you can have both atoms going back and forth at the same time. And that's called a symmetrical stretch. Then you can have both them going on opposite times. That's an asymmetric stretch. You can also have them bending in and out of plane, or rocking back and forth, or wiggling, or even twisting out of plane. All of these are still absorbable vibrations because it's causing molecular motion. However, most of the time, these are the lower energy vibrations, and we'll see them in what we call the fingerprint region, okay? We have a couple of these we do see in that higher range, but only with the hydrogens. So the most important thing we want to think about here is that absorbing energy creates those vibrational modes that allows us to observe these through IR spectroscopy. Okay, now the take-home slide of this lecture is this slide, okay? So, but I want to walk you through it and show you that, look, nitrogen, oxygen, and carbon hydrogen bonds are all in that same region, okay? And those are the only bonds you're going to find in that region, from about 2800 to about 3500, okay? They have different shapes, and I'll show you that later, but only these hydrogen and other atom bonds show up in this area. Then of course, so if that's the highest frequency one, and that's by mass, the next highest frequency one is going to have to be by bond strength. So the next zone we look at is this 2100 to 2300. It's our triple bonds. That's the only thing that shows up in that range, okay? And it has everything to do with that bond strength, giving it a higher frequency than a double bond and a higher frequency than a single bond, okay? So that means the next zone we need to look to is about 1600 to a little over 1800, and that's where we find all of our double bonds, our carbon-oxygen double bond, our carbon-carbon double bond, and our carbon-nitrogen double bond. And then usually we can actually see a bunch of things to around 1,000. This right here, things above 1,000 are useful in helping us identify functional groups. Things below 1,000 are where those other wags and wiggles are and are less important in identifying our functional groups, okay? So if we have a peak in this 1,400 to 1,000 range, we're looking for a carbon-carbon single bond, carbon-oxygen single bond, carbon-nitrogen single bond. And if you have different types of carbon-carbon, so you have a primary carbon to a secondary carbon to a secondary carbon to a primary carbon, the secondary carbon to secondary carbon might have a different frequency than the primary to secondary carbon. So we're actually going to see more than one peak in this range as the molecules get bigger. Okay, do we understand the different zones? Knowing these zones and what shows up in these zones is the key to identifying compounds by IR.
So how come like there's only carbon, nitrogen, and oxygen? Are these because they're normally seen in the functional groups?
Those are the easiestly to recognize functional groups in IR.
Okay.
There's also the carbon halogens are down here, but they're typically below 1,000. Okay, the x-axis is our wave numbers. The y-axis is our percent transmission. So let's say we had something with no, we're going to have a compound that it only has a triple bond in it, okay? So what we're going to see is that nothing's going to absorb. We're going to have 100% transmittance until we hit that zone, and then we're going to have maybe nothing else. So if we only had a carbon-carbon triple bond with nothing else, we would have no other absorption anywhere else, and only that happens, okay? So that's why we have percent transmission on the y-axis and the wave numbers on the x-axis, okay? Okay, so that being said, let's kind of try our thing. The first thing I want you to do is I actually want you to look at the compound and try to figure out where bonds might be. Now, don't forget, we need to add our hydrogens here, because we have our stick figures always have hydrogens wherever you have here. So the bonds we're looking for are going to be carbon-hydrogen bonds, and they're going to be in that high range, that around 3,000 range, okay? And but we also have an OH, but we also have carbon-carbon bonds. So we should see 3 types of bonds above 1,000, okay? So above 1,000 right here. And we see an OH, which is in that 3,000, around 3,000 range. Notice we see nothing else on this whole middle range. We don't have any triple bonds. We don't have any double bonds. Nothing absorbs in that range, okay? Then right below 1,500, this might be one of the carbon-carbon bonds, or maybe the carbon-oxygen bond. And then this could be a carbon-carbon bond, carbon-oxygen bond. So once you get below 1,500, it's harder to identify functional groups, but you should be able to see the groups that are specifically the single bonds between carbon-oxygen, carbon-carbon, and carbon-nitrogen. So just by looking at that, we can tell we are going to look for 3 types of things, but this OH and this CH are the strongest and tell us the most. Okay, note, we have aliphatic hydrogens, sp2, sp3 hybridized carbon gives us hydrogens below 3,000, okay? sp3 hybridized carbon-hydrogen bonds are below 3,000, okay? I'm gonna show you why in a couple minutes. Okay, let's move to the next one. So now we have a nitrogen-hydrogen bond, and it's also gonna show up in that same region, okay? And typically, if you have 2 hydrogens here, you get 2 peaks. If you have 1 hydrogen here, you get 1 peak. And if you have no hydrogens, you get no peak here at all. All right, let me talk about the line shape up here. See where this hydrogen has this broad line and these are sharp? These other peaks are sharp? And the OH has a broad line and the other peaks are sharp? Because of the oxygen and nitrogen, their hydrogens can hydrogen bond. And because they can hydrogen bond, that gives them a broad range of absorptions available to them. So you always have a broad peak. Okay, so notice that the carbon hydrogen does not hydrogen bond and we have nice sharp peaks. And we probably have a nice sharp peak for each type of primary, secondary, or tertiary carbon hydrogen there, which is why we have multiple peaks in that range. Okay. So, and what we say, we have the same hydrocarbon place, and so we have that same zones where we have our carbon-carbon bonds, and then it gets about right here is 1,000, so we start seeing maybe our carbon-nitrogen bond and our carbon-carbon bond down here as well. Okay. All right, do we see by just looking at the different types of functional groups, we should be able to find them in those different ranges. Okay, pause and go. All right. Okay, so I said that the peak will change based on how many hydrogens you have on that nitrogen. So in the case of 2 hydrogens on a nitrogen, you get 2 peaks. Notice it's still a little bit broad here, but it's not as broad as that OH peak. The OH peak is by far the broadest of these peaks. If we take just 1 hydrogen here, we get this. And so we have 1 peak for that 1 hydrogen. So that's telling us that these 2 hydrogens that are on here are probably not exactly identical, or they have a different vibrational mode. Okay. Once you take that hydrogen off, this peak goes away. So now you can identify your primary mean, your secondary mean, and your tertiary mean just by looking at the 3,000 range. Okay. The other thing I want to draw your attention to is notice that all of these are aliphatic. And if we draw a line down here, all of the peaks are below 3,000 right here. And as we get more and more complex, we start seeing more and more peaks in that range. But they're all carbon hydrogen peaks. Okay, so I said it was very important that the bonds we're seeing at below 3,000 are all sp3 hybridized carbons, okay? That tells us that we have the difference between an alkane, an alkene, and an alkyne, okay? So our alkanes right here are all gonna show up below 3,000. And it has to do with the idea that that bond between the carbon and the hydrogen is actually longer because of the amount of P character in that bond. It's only 3/4 P character, 1/4 S character, giving us a slightly longer bond and a lower energy. That lower bond strength gives us a lower frequency. When we go to our sp2 hybridized system here, we're 2/3 S, 1/3 P. That's giving us a shorter bond length and a higher bond strength. And that shifts our alkene hydrogens just above 3,000. So that's a great way to tell the difference between an alkane and an alkene, just in that 3,000 range. And if you have a hydrogen on the end of your alkyne, it's going to show up way up at 3,300 because we have half S and half P, giving us a shorter bond, giving us a stronger bond, giving us a higher frequency. Okay, so do we see that these characteristic CH stresses still agree with our higher frequency equals higher bond strength? Even though this is, not the triple bond or the double bond, we actually have that hybridization changes that bond strength. And so we can recognize that when we see it in a spectrum. And to prove that, I'm going to go ahead and pull up a spectrum and show you that we can. Okay, so let's look at octane first, right here. In theory, octane only has carbon-carbon bonds and carbon-hydrogen bonds. So let's look at the carbon-hydrogen bond region, which is right around 3,000. Notice that there's not a single peak above 3,000. All of them are below 3,000. And we have a couple different types of carbon hydrogens there. Okay, and so that's why we have a couple different peaks. However, if all we do is take away 2 hydrogens and turn it into the alkene now, we are now going to have 3 hydrogens on that alkene, and they will show up above 3,000. So notice we have our first peak above 3,000. And on our, if we take 2 more hydrogens away and turn it into the alkyne, we now shifted up to 3,300. Okay. Now, the strength of this peak varies, and I'll talk about that in a minute, on how polarizable that double bond is. If it's very symmetrical double bond, it might not have a very polarized bond and we might not see it. However, because this has 2 hydrogens on this side, 1 hydrogen and a carbon, it is polarizable and we do see it. Okay, so that's with the hydrogens on sp3 hybridized alkanes. However, there's one more type of hydrogen we have, and that's the hydrogen that we have bonded to a carbonyl, an aldehyde hydrogen. Okay, the aldehyde hydrogen is actually quite unique in the fact that it's bonded to an sp2 hybridized carbon, but it's double bonded to an oxygen instead of a carbon. That changes the polarizability. That changes the bond strength. Okay, when we do that, we get a distinct peak at 2,700 and 2,800. Sometimes both, sometimes just one. But if you see a peak, nothing else absorbs down to that 2,700 range. If you see that peak in 2,700 and it's nice and strong, and stronger than the baseline here, you might have an aldehyde. Okay, so those are the 4 different types of carbon-hydrogen bonds we have to us in the functional groups we know right now. And we can differentiate them just by looking at that 3,000 range, and we can tell the difference between them. All right, questions on hydrocarbons, hydrogen-carbon bonds in IR. There's 56 of us here, so I'll move on. Okay, so now we have a really good grasp of looking at that carbon-hydrogen bond, that high energy thing. Let's talk about some other double bond systems first. Now, the carbonyl right here moves around quite a bit depending on what's attached to it, what's in this X and Y position here. But in a ketone, we call that kind of like the baseline. Everything moves up or down from that because it has 2 carbons on it, and that's a fairly low, that they're not pulling or pushing electron density away from that carbonyl. So we call that kind of our ground zero, and we're going to move up and down from there. Notice that this is a very strong bond, okay? This is a permanent dipole moment, meaning it's already polarized. It will always absorb strongly in this range between about 1650 and about 1820. That is where you're going to find all of your carbonyls, and they are all strong intensity. Notice we also have our carbon-carbon bonds way over here. But let's move on. So I said that moves around, that carbonyl moves around. It has everything to do with whether or not there's an electron withdrawing group or there's a resonance stabilization in the system. If you have a resonance stabilization in the system, like forming the acetate ion, you're actually going to decrease the bond strength because you're sharing that bond over multiple atoms, and it has a lower frequency. Okay? The electron withdrawing group, like let's say we put a chlorine on there, is going to increase the bond strength and therefore will shift the absorption to a higher energy. So what does this mean? Well, let's look at all the different types of carbonyl functional groups we have and put them in order of highest frequency to lowest frequency to demonstrate this problem. Okay, so the first thing I want to do is I want to look at a very electronegative atom, chlorine. That's the most electronegative atom we have here, and therefore we have chlorine is going to give us our largest change in our shift. It's going to move to higher frequency. Okay, so we actually have it way above 1700, which or 1720, which is where ketones are, up to this 1850 to 1790. Okay, so that's the highest we're going to do because it was, and in fact, if you had a fluorine there, it might shift a little higher. But the halogens are definitely the highest electronegative atom we're going to have here, and that means it dominates. Okay, notice that we can't really draw a resonance structure with chlorine, having the negative charge on chlorine or the positive charge on chlorine, because it would actually be dissociated. So we do not see any resonant effect. Okay. The next thing over is the ester right here, and it has a little bit of an electron withdrawing effect because of that other oxygen being only having a single bond to it. And it has a little bit of a resonance effect as well because we can spread out over here. But the electron withdrawing effect is stronger, and therefore it's shifted higher to that. Remember, resonance shifts it down, electron withdrawing shifts it up. So that electron withdrawing shifts it up higher, above that 1720 for ketones, to that 1750 to 1735. The aldehyde is also right here, not very, it's that hydrogen is not really that electron withdrawing, but it's not electron donating like the carbon can be. So we actually have it just a little bit higher than that 1720 to 1740 range. That's where we see those aldehyde carbonyl shift. This is our baseline, of course, ketone. This is right where it says it can stabilize a little bit through hyperconjugation, but that's really what I would consider our neutral species at that 1700 to 1710. And then let's change our functional group again, and let's go to something that actually can have a strong resonance contributor. In the case of the amide, that nitrogen is also electronegative like oxygen and have a strong resonance contribution. And notice our frequency drops below 1700. So that is a definite strong contributor there. But the one that's even more delocalized is the full carboxylate ion or the acetate ion, like example, shifts it all the way down to 1610. And then there's another peak way down here at 13 to 1400 we typically don't see. But having that be the lowest frequencies we have in our carbonyl compounds gives us a lot of power for identifying functional group just by looking at where that peak falls, okay? And if you don't want to memorize the numbers, you have to figure out, is that electron withdrawing or is it resonance stabilized? Electron withdrawing is going to be higher frequency, resonance stabilized is going to be lower frequencies, with ketones being our baseline right around 1720 to 1710. Questions? Okay. All right. So let's apply that with two compounds here. Okay. So I said resonance effects will lower that frequency, right? Okay, it's not necessarily just the one that we see in that carboxylic acid salt. If it can be resonance stabilized over using a double bond to help extend that charge over, that will also act as a resonance stabilized carbonyl and will shift it down in frequency as well. So let's look at the first one up here, this ketone. We have a nice strong carbonyl right here at 1718, which is right at 1720, right? We expect it. We have, of course, our carbon hydrogen bonds here. And notice they're all aliphatic, so we only have the ones and they're all above 3000. And then we have some different types of carbon-carbon bonds and that we see here. Okay, that's what we see in that region. But remember, we're identifying our functional group just from that 1500 to 4000, and we look for those carbon-oxygen and carbon-carbon bonds below 1500. In the case of our adding a double bond here, now we can resonance stabilize some of this charge out with that double bond. And look what happens to our carbonyl. Our carbonyl shifts below 1700, and we see the growing end of that new carbon-carbon bond right at 1600. So we can differentiate between just a regular ketone and a conjugated unsaturated ketone, where we have just added an alkene to the system, and that'll delocalize the charge. Okay, so why do I say it delocalizes the charge? Well, what we can do is we can look at how we delocalize things by pushing electrons around in our Lewis dot structure. So we have an opportunity to take the two electrons from the double bond, switch it to the next carbon over, and then put these electrons up on that oxygen, giving us a separated charge of plus and minus. So it's perfectly valid state, Lewis dot structure state. But then, of course, it would want to have this come back in and go back out. But the point is that we have this resonance, two possible resonance structures that are both valid. And we know that this happens because of the shift in the carbonyl in the IR. Questions on that? Okay. All right, now let's talk about double bonds and where they would show up. So if you have a double bond, carbon-carbon double bond, and it's not polarizable, meaning that it's like a net dipole of 0, sometimes that carbon-carbon does not show up, okay? So, but let's look at the top side first. We have a lot of sp3 hybridized carbon-hydrogen bonds. We have alkenyl hydrogens right here. Those are above 3,000, but there's no carbon-carbon absorption at that 1,600 space. The reason is that the net dipole on this structure basically cancels itself out. We have 2 carbons pulling equal and opposite each other, 2 hydrogens pulling equal and opposite each other, and that double bond is not polarized, so we don't see it. It's harder to see if the bond is not polarizable. That makes it harder to absorb. However, when we switch from the trans, where all of them cancel out, to the cis, where they don't cancel out, we have the carbons are more electron withdrawing in this range. The hydrogens are slightly less in this range, giving us a net polarizability in this direction, meaning we will have a better time at absorbing in that bond, and we see our peak right here at 1668. Okay. Remember, it's between 1600 and 1700. And again, we have a peak above 3000 showing us our alkene hydrogens. Okay. So let's take that one step further and add a very polarizable group on there. We're adding a chlorine to this side, which is really, really strong. Our net dipole is going to be in this direction because of that strong electronic group. And we see a much stronger peak right here. See how this peak isn't as big because we have these kind of running off the screen here. We actually are showing them almost as strong as the carbon hydrogen peaks. And that's important to show you that that polarizability will affect the intensity of our carbon-carbon double bond peak in that 1600 to 1700 range. Also, we have our alkenyl hydrogens there. Questions on that?
You said polarizability will affect.
Right. The more of a permanent dipole you have on your carbon double bond, the stronger an absorption it will have. Okay?
And by stronger absorption, you mean like more?
Larger, the peak will be larger. The peak will get closer to the baseline.
Okay.
Okay. So the more it absorbs, see, so this is like right here, this is 10% transmission. That means it absorbed 90% of that wavelength of light. Here we have it about 30% transmission. It absorbs 70% of that wavelength of light. So right over here, this is only 70. So it only absorbs 30% of that light. So just that jump in polarizability goes from 30% of the light to 70% of the light. Okay. You see what I mean by more intense peak? All right. So let's look at the triple bonds and see if we see a similar thing happen to it. Okay. It does. So if a triple bond is symmetrically substituted with either carbons or hydrogens, the peak for the alkyne actually shows up very low. In this case here, we have almost no peak at that 2000. Remember, that's in the 1900 to 2200 range are those triple bonds right here. But what we do see is we also don't have any alkynyl hydrogens here. There's nothing in that 3300 range. And that means that that peak might be hard to see because it's not polarizable. Just by taking it and adding a hydrogen to it, now we have a different pole in each direction. Now we will see that triple bond peak, and it's a nice strong clean peak at that 2100. We see our sp3 hybridized carbons, but then we see our nice strong alkyne hydrogen right at 3,300. See how strong that is? Nice, almost as strong as just that one hydrogen is almost as strong as all of the others together. Okay. Now let's look for that in the nitrile. Nitrile is always polarized and typically has a fairly strong, at least moderate to very strong absorption in that range. Okay. So those are the only those are the only two functional groups that show up in that 2000 to 2200 range of the IR spectrum. Questions? All right, let's move on to another functional group. Okay, the next functional group I want to talk about is benzene. Okay, we don't actually study benzene till next semester, but it has some unique characteristics in it because we have alternating single and double bonds in the same structure. And what that gives rise to is we have carbon-carbon bonds that may or may not be polarizable, and we have carbon-carbon double bonds that may or may not be polarizable. But they have a unique system in the fact that because these are alkenyl, all of the hydrogens are going to be above 3,000. And we have this really weird pattern here. So this is that idea of the carbon-carbon, single bond, double bond, single bond, double bond, overlapping and kind of going around and around all the time, gives rise to this sawtooth pattern we call overtones. Those are those carbon-carbon bonds, carbon-carbon double bonds that show up there. And then we see our carbon-carbon double bonds barely, and our carbon-carbon single bonds show up a little bit stronger. But our carbon-carbon double bonds, because they're constantly flipping around, are shown as overtones. Okay, so you'll see that. All right, so let's talk about the intensity versus functional group. Okay, the OH is typically very strong and very broad because it can hydrogen bond. That's why it's broad, it's because it's a hydrogen bond, and it's a very polarizable bond. The nitrogen-hydrogen bond actually has a couple different things it can do. It does a stretching, and if it has two, it'll do two peaks stretching at the 3,000 range, but then there's also something we can see in the 1,500 range as well. That's a lower energy frequency where it's bending instead of stretching. So the stretching frequencies, the two rocks on a string, is the stronger intensity and higher frequency intensity. Excuse me. Okay, so then the alkanes and alkenes and aromatic hydrogens are variable. They tend to be moderate, but they can get stronger or go away depending on polarizability. When we do have that alkynyl peak, it tends to be very strong. I'm sorry, when the alkynyl peak, it tends to be very strong and narrow. The aromatic hydrogens, the sp2 carbon hydrogens, are also variable in intensity as well. Aldehyde is usually strong and unique in that 1700, 2700, and 2800 wave number position. Okay. Carbon-carbon triple bonds are typically weak because of that polarizability. The carbon-carbon double bond is usually can be varied by what's attached to it. The more polar things on it, the more it will be showing up. The less polar things on it, or the more symmetrically, it will be last. Nitrile is variable, but tends to be fairly strong, at least half to, moderate to strong. Carbonyls are always strong. Imagine, permanent dipole, always strong. So notice these are all strong. All the carbonyls are right here. The only difference in the carbonyls is we shift based on whether or not we have what kind of electronic drawing function we have, or what kind of resonance contributor we have. The more resonance, the lower the frequency, the more electronic drawing, the higher the frequency. Then we have our carbon-oxygen bond right here at 1,000 to 1,200. It's actually fairly strong, and most of the halogens are strong, but they're all below 1,000, so sometimes they're very difficult to pick out from other things. All right, questions on functional group versus intensity. All right, so let's put some of that to practice, okay? So let's look at methanol right here and formic acid right here, okay? So Right away in the methanol, we see carbon-hydrogen bonds. We have no carbon-carbon bonds, but we do have a carbon-oxygen bond, and we have an oxygen-hydrogen bond. So we're looking for 3 types of bonds to find, okay? So when we look at that, the OH right here, because it's an OH, has a broad peak. So we see our big broad peak at 3,300. That's our OH peak. We can identify that clearly from that. Right here, we have aliphatic hydrogens right here. sp3 hybridized carbons with hydrogens on them here. Basically not much else until we get to this strong carbon-oxygen peak right above 1,000. Okay. We don't expect to see any carbonyl because we don't have a carbonyl. We don't have any triple bonds, double bonds, etc. So we have all the expected peaks. Now let's take a almost similar molecular weight type material and basically take that methanol and oxidize it down to formic acid. So now we have an aldehyde and we have a carboxylic acid, and now we have a carbonyl. So let's look at what we see there. The first thing we see is that our OH peak is shifted down. If the alcohol is up here, carboxylic acids are shifted down and overlap that entire region. Anytime you see that big broad peak that overlaps that 3,000 mark, you're looking for a carboxylic acid. Okay. Now, because of this overlap, you can barely see our peak at 27 and 2800. Although they're very difficult to see because of that broad peak. So it'd be hard to say for sure you had an aldehyde there. But when we look at our carbonyl compound here, we have a carboxylic acid, so that should be shifted lower, but we have that aldehyde, which shifts it higher. So it's somewhere in the middle from having the carboxylic acid at 1680 and that aldehyde at 1750. So we're right in between the two. So we have a push and pull working on us there. And then this is probably our carbon-oxygen peak here, single peak. And then this is, those are harder to identify, but those are definitely there. So look for the functional group and all the functional groups you have available to you and string them all together. All right, so that tells us we have to have a strategy for identifying compounds by IR, and we do. Okay, you want to identify the most intense absorption peaks on the spectrum first, okay? Especially those outside that fingerprint region, things above 1,000, okay? Just because there's peaks in that 1,000 to 1,500 range, it doesn't necessarily make it easy to assign. So let's assign the ones above 15,000 first, and then maybe look for things in that 15,000 to 10,000 to, 1,500 to 1,000 range, and then we can do that. Now that we have those most intense peaks above 1,500, let's figure out what possible functional groups we have. Is it have a carbonyl and it looks like it has a carbon-oxygen bond, but it doesn't have an OH? It could be an ester. Look for, those two things that are only in the 2,200 range, the alkyne and nitrile. So then start considering the possible formula. Are there double bonds present? Do we have a carbon-carbon double bond? Do we have a hydrogen above 3,000? Do we have that peak at 1,600? Start looking for the different things. And then by looking at assembling your functional group to make sure that all of the intense peaks are included in that functional group, you should be able to identify that. Okay, so I think that's my last slide on this. So using this strategy, you can go ahead and do the homework for that second section, module 2.2 online, and you can start to look at that saying, okay, I have these 3 peaks. Okay, so I can't have an alcohol, I can't have an amine, I can't have this, because you can start excluding functional groups when you don't see them absorbing in their ranges. And then you start to assign based on what you do see. Okay, questions on that?
Are you about to go over some examples?
No, that was all the examples were already in the system. Yeah. But I wanted to summarize with the idea that's the strategy I was using each of those times. I was looking for the most intense groups. I was assigning those most intense groups, and then to do it backwards in the homework to get comfortable with being able to assign functional groups by just looking at the IR. Okay? But in the future, maybe I will add a couple examples. So let's go ahead and shake it off, take a break. I'm gonna stop sharing temporarily and bring up my slides for our next chapter, chapter 3. All right. There we go. Moving on. Okay, so I'm going to go ahead and pull up my screen here. And do you need to memorize all the ranges for the groups? If you don't want to memorize the ranges for all the groups, be able to identify where they should be based on their bond strength or their atom size, mass. So I would let that, like I said before, that slide where it had all the different types of bonds showing up in the bunch of ranges, kind of, if you can understand, memorize, or be able to quickly assign all of those to their different ranges, that's what you need to do in IR. Okay? Okay, so module 3, that's where we're on the schedule, so might as well start there. Acids and bases. So traditionally, we've learned a lot about acids and bases in inorganic chemistry, but we have to approach it a slightly different way in organic chemistry, okay? So the idea here is that we traditionally learned that an acid was something that dissociated in water and formed hydronium ion, and a base was something that formed hydroxide in water, okay? That's the Arrhenius definition of acids and bases. However, we don't use a lot of water in organic systems, so we have to have a different definition. So the definition I want you to put to memory is this. A Lewis acid is a substance that can accept a pair of electrons, usually to make a sigma bond. Lewis acid can accept a pair of electrons to make a sigma bond. That means, in contrast, a base has to be able to donate that pair of electrons to make a sigma bond. Okay, so let's look at that in this example here. Okay, so our boron only has 6 electrons in its outer shell, so it can accept electrons from a system, okay? Our lone pairs here on our water can donate them to create a new sigma bond. And when they do, those electrons are the ones that create that sigma bond here. And we now have our new acid-base complex where the acid accepted electrons from the base to make a sigma bond. Okay, now this doesn't necessarily have to be a one-way street. There is typically an equilibrium related to these systems. Okay, so in this case, we went from 2 neutral molecules to a double charged species. Okay, but it can go back to those 2 neutral species. All right, let's look at it in a different way. Let's look at it over here. And again, we have a Lewis base. Now, when you're looking for Lewis bases, look for the thing with a negative charge or lots of lone pairs. Those lone pairs can be donated to create a new sigma bond. Okay. Now, in this case here, we have our sulfur anion acting as our Lewis base. It's donating electrons to this carbon. Why is this carbon a Lewis acid? Well, it has a polarized bond with this bromine. This bromine is pulling electron density away from it, the carbon, toward the bromine, making this carbon partially positive. That's why it's the Lewis acid, because it's already partially positive because that polar bond. And so what can happen is these electrons come in, create a new sigma bond here, and it also generates the bromide ion. Okay, so our bromide ion now has a negative charge. It's now a Lewis base. It has electrons. It's ready to donate and share. Okay, and it's not as polar, but we still have a polar bond with the sulfur pulling a little bit of electron density away from the carbon, making this also partially positive, which makes it a Lewis acid. Okay, so convert this to Lewis acid, Lewis base, and the ability to accept an electron pair is acid, the ability to donate an electron pair is a base. Okay, so how does this fit in with our more traditional thing of transferring a proton? Well, in organic chemistry, instead of using the water-based system, we use what we call the Bronsted-Lowry Acid-based theory. In this case, we're still transferring a proton, but it can be in the absence of water, okay? So a Bronsted-Lowry acid is a substance that can donate a proton, okay? So that's an important thing, which makes the base the opposite is the one that accepts the proton, okay? So in this case here, we have acetic acid and we have a hydroxide ion here. So we're going to transfer this proton to the hydroxide ion. And when we do, we get water and we get this anion formed by the acetate. Okay. So what just happened? Our acid has now become our base, and we call that our conjugate base because it was the acid and now it's the conjugate base. Okay, that's important. This was our base. Now it actually has a proton it can transfer. So now it's our conjugate acid. So our acids always become conjugate bases. Our bases always become conjugate acids. Why is this important? Well, we need to know something about these pairs to allow us to know whether or not the reaction is going to go and how far the equilibrium is going to lie in this system. Okay, so let's dig a little bit deeper into acids and bases and think about what we know about acid strength. Okay, so in the case of, oh, I didn't erase that. In the case of acid-base reactions, the stronger base will always win the tug of war with the proton, okay? Which means you're trying to go from the strongest acid and base to the weakest acid and base in the system, okay? So think about that when we have a very strong base, it's going to shift the equilibrium into the product side or the proton transferred side of the reaction. So in this case here, because the hydroxide here is the stronger base, it's going to pull it away from here, creating our new conjugate base and our new conjugate acid. Okay, so that means that if it's stronger base going to the weaker base, we're going to shift in that direction, which means the equilibrium is going to lie toward the deprotonate carboxylic acid and the formation of the water. Okay, but how can we tell? How are we going to know which is stronger and which is weaker? Well, we have to have a way to do that. And traditionally, when we had water in our system, we had what we call the pH of a system, right? We could find the pH of a system because we would know the concentration. Oh, I can't believe I didn't erase this. All right. We had the concentration of our proton, our conjugate acid, our conjugate acid, our conjugate base over the concentration of our acid, okay? And if it was going to a low number, that means we had the acid was completely dissociating and we have a low pH. If we go the opposite direction, we have a high pH. Okay. So in general, that's why our acidic solutions are 0 to 7. But if we start going the other way, so we're making more hydroxide concentration, this is going up, that number is going to go up, and we actually end up with a pH above 7 and up to 14. Okay. And that's in the presence of water. We only have that 0 to 7 range in water. Okay. But that total difference of 14 is important. So remember, pH plus pOH is equal to 14. Okay. That's going to be true in the absence of water as well. So what does this mean? Well, so our pH is something with a strong acid. And so what we can do is instead of calling it the hydrogen, let's just look at the equilibrium constant between whatever the conjugate base was. If we look at it that way, we can have what we call our equilibrium constant for our acid or our Ka. Yes.
Up.
Hello?
Up.
I heard a couple chirps and nothing else. Oh, okay. So no question? So that means if we have a very high concentration of hydronium or hydrogen in the system, we have a high pK, we have a high equilibrium constant, which gives us a low pKa. If we have a low number, so this is like 0 and below, and then if we have a weak acid, we're going to have a high K number or a positive number all the way up to 50 in our new system. Okay. But the important thing is that our pKa plus our pKb is always equal to 14, which means when our pKa's are outside that 0 to 14 range, we can still see the strength of our conjugate base. Okay, so let's talk about that in a little more detail because I think it's important that we identify what we mean. And in organic chemistry, we typically take one or the other, the pKa or the pKb, and look at both sides of the reaction and see which one's the stronger acid or the stronger base. Most of the time, we're going to use pKa's, except when we talk about amines next semester. So what I want you to do is focus on this pKa side of the chart and look at some trends here, okay? So the first trend I want to look at is way down here. And as we know, HBr is a strong acid. It's a traditional strong acid from inorganic chemistry. In fact, HBr has a pKa of -9 in the absence of water in this scale. So it's a very strong acid. Everything below 0 is what we call a very strong acid, or as you approach 0. Okay. So that means the hydronium ion is also very strong at a -1.7. See, these are different numbers than we saw on the pH scale. So we need to make sure that we're looking at the pKa of these different organic compounds, because that only works with hydronium ion. Here we're going to be protonating other species. So here we have our set of carboxylic acids. The first one we brought a baseline here is the acetic acid. Our carboxylic acid is at 4.8. Okay, so you might want to memorize this or learn it, that's kind of where our starting point is. Then as we change, as we go up, we have protonated ammonia is at 9, and phenols are here at 10. So we're going to learn this group a little bit more next semester, but that's just an alcohol with a phenyl ring on it. Then when we go from, if we look at water, water is actually acidic or basic, right? But it has a pKa of 15.7. That's one you're going to want to memorize. So definitely memorize everything in blue here. Right here. And then we go to alcohols. Alcohols are almost like water. They're slightly higher pKa, which means they're weaker acids. When we go up to a carbonyl with a hydrogen here, that hydrogen actually can be acidic. It has a pK of 20. And then the next most important ones will go when we have an alkene right here. I'm sorry, an alkyne right here. It goes up to 25. An alkene, it goes up to 43, and our alkane is all the way up at 50. Okay, so those are the numbers you want to pay attention to, the ones in blue. Okay, and we're always going to compare pKa's until we talk about amines. So remember that. So if that very low number is very acidic and the very high number has to be the opposite of that, so it's a very weak acid. Okay, so the cool thing about that is that base strength is exactly opposite of acid strength. So our very weak acids up here, in here, become very strong bases. That inverse proportionality is very important in our system, so that if you have something that has a very high pKa, it's going to be a very strong base and try to react with things very rapidly. Contrastly, once we form this right here, like this strong acid right here, we get this bromine ion. It's a very weak base. It wants to be a negative charge. It wants to be fine. So it's going to be a very weak base. So everywhere is also the same. So our alcohol here, once it's a kind of a weak acid, but once you deprotonate it, it's a strong base. It's like hydroxide. So the alcohol with a hydrogen there is stronger than the hydroxide ion because it was the weaker acid. So get that kind of straight in your head, that a A very weak acid is a very strong base. And so you need a very, very strong base to even stronger base to remove hydrogens from those acids. Okay, questions about that inverse proportionality between very strong acid and very weak base? Or very weak acid and very strong base? Okay, so let's put this into a little more perspective in the kind of a little bit of why, okay? So I said before that a low number, like a negative number, is a very strong acid. pKa's that are negative are very strong acids. And then most of our organic compounds are going to be above 0. And they vary based on their structure. So here, let's compare our very strong acid right here. Oops. Our very strong acid here, HCl, -1, okay? So what does that mean? If we take that HCl and donate a proton, we become a conjugate base, right? And that conjugate base right here is the chloride ion, okay? The chloride ion is actually a very weak base because this was a very strong acid. Let's move up to acetic acid. We've got that pKa in that 4 range. This is a stronger base than the chloride, but a weaker base than hydroxide. Okay. When we have water, it had a pKa of 15.7. It made the hydroxide ion, which is a stronger base than the one below it, but a weaker base than the one above it. Okay, do we see how that kind of works together? So by the time we get to alcohols, this is going to be less basic than making an alkynyl acetylene ion because the pKa is higher. Once we go to alkenes, we have 44, which makes this a much better base than that. And when we get to the alkanes, those are very high, 50 to 55, sometimes even 60. This is like the strongest base on our page right now. Because it was the weakest acid, it became the strongest base on our page. Okay? So why do we care? The pK values can tell you which way the equilibrium lies. The way you do it is you compare the pKa value of the acid on the one side of the equation and the conjugate acid on the other side of the equation. Whichever was the stronger acid, it is going to be shifted to the weaker acid. Okay, so let's apply that with acetic acid in the presence of hydroxide here. If we look at the pK of acetic acid, it's 4.75. Okay, the conjugate acid is this water molecule here, and as we know from our chart there, our water has a pKa of 15.7. Okay. So if our pK of 15.7 makes it a weaker acid. So in which direction, right or left, is the equilibrium going to lie? Type. Okay, it's going to lie in the weaker acid. So it's going to lie in this direction toward the acetate ion and water. Okay, that's true for any system, even things that don't have water in them. For example, you can have vastly different ones right here. We have acetylide ion in the presence of water, making it the acid, and it has a pK of like 15.7. And then if we look at the conjugate acid here of that acetylene, it has a pK of 25. So that means that it is going to shift toward the weaker acid. So we're going to have more of this. And there's such a big difference here, greater than 10, it's going to tend to shift it strongly. The bigger the distance or the weaker the acid, the more it's going to be shifted to this side with very little, if any, measurable equilibrium reaction. Okay, so stronger acid moves to the weaker acid. Yes. Okay, so let's see where we are. We're at 40. We go till 150. Yes. All right. So now let's talk about what makes things stronger or weaker, and as far as the acid goes. Okay. So the reason we want to look at this is that we want to see the different ways of seeing whether or not your reaction is going to go or not, okay? Because you're always going to want to go to the weaker side, so you have to identify which they are, okay? So the first step in understanding the acid-base reaction is there must always be that acid-base pair, okay? If the reaction in the water sometimes is just not shown because there's so much of it around, but in the absence of water, you have to look for what your base is. In this case here, we need to have our base on one side that turns into our conjugate acid. I'm sorry, our base turns into our conjugate acid. Sorry, pointing the wrong one. Okay. And our acid has to turn into a conjugate base on the other side of the reaction. So knowing which is the acid and which is the conjugate acid, which is the base and which is the conjugate base is the first step in understanding. Okay, so how does this transfer of proton work? Well, just like in that Lewis acid definition, some atom is going to be accepting electrons, that's the acid, and some atom is going to be donating electrons, that's the base. Lewis acid, Lewis base. In the case of transferring protons, we actually can use the Bronsted-Lowry where we're transferring a hydrogen. So our hydrogen here is our Lewis acid. Okay, our Lewis acid part right here is the hydrogen, and our counter ion here is the base. We had a sigma bond here. We're going to break that sigma bond and leave those electrons behind. The protons from the OH group, from the oxygen are going to create that new sigma bond and transfer that hydrogen, which means our acid right here becomes our conjugate base, and our base becomes our conjugate acid, but then we can go back and forth, okay? Notice that the base is on both sides of the reaction, is donating electrons to form that new pi charge. So that Lewis acid description is valid for both sides of it. The stronger base will form the stronger bond, and the proton will win the one that forms the stronger pi bond wins the tug of war. So basically the one that's the stronger base is going to pull it away to make it the weaker acid. So the weaker acid-base pair will be the predominant system in equilibrium. The driver of the equilibrium. All right, so that means acidity depends on the stability of that conjugate base. The more stable that conjugate base is, the more acidic that proton will be, because my base is not very, my conjugate base is going to be a very weak base, or it's going to be a delocalized base, or it's going to be nice and happy as that anion. So acidity depends on the stability of that conjugate base. Okay? Acidity increases with that increasing conjugate base stability, which means if you had something that was not stable as that conjugate base, it's not going to be very acidic. Okay. So when we think about these equilibriums, think that strong acid, you're going to go from that strongest acid to the weakest acid in our system. Okay. So stronger is better, but what makes one acid more stronger than the other? Well, it has everything to do with that equilibrium constant as we compare the conjugate acid concentration here to the conjugate base concentration over the concentration of acid. So as that concentration of acid goes down, that Ka goes up. Excuse me. All right. So think about it as this concentration goes down, this number goes up, and our pKa goes up as well. Okay. So, what makes the conjugate base stable? Okay. So let's talk a little bit about the conjugate bases here. And we're going to, Okay, I'll do one part of this right here. So there are 4 factors that we want to deal with when we're talking about the acidity of a compound, okay? And we have to directly look at the strength of that conjugate base based on it. So all of these are going to be talking about the conjugate base. Is the conjugate base happy or stable, or does it have some effect that makes it want to give up the proton more? Okay, so there's the electronegativity, or the size of the atom the hydrogen is bonded to. That's one, and I'll talk about that. Then on next lectures, we'll do resonance or delocalization of charge. And then there are some inductive effects. You can actually pull electron density through bonds and change the acidity of something. And then the hybridization of the atom will actually change the acidity as well. And we saw that going from alkyne to alkene to alkane, and I'll explain that further. But now let's talk about electronegativity and size of the atom, okay? So in general, acidity always increases with the increased conjugate base stability, meaning the anion formed in the reaction, the more stable it is, the better it is. So if you have a more electronegative atom, it has a greater ability to stabilize that negative charge and be happy. So the stronger the electronegativity of the atom, the more likely it is to be stable as that ion and therefore be a stronger acid. Okay. However, it has to be compared with the size of the atom as well. Okay, so let's look at just the ability using electronegativity right here. All right, and if we look at just electronegativity, and let's look down our string here. Let's go in this direction here. So fluorine is our most electronegative atom, and so we would expect this to have a fairly good bond, a very strong bond, but polar bond, and it's going to be have a pretty decent stability as an anion. Okay, so fluoride ion, that's very common. We see it all the time. So we're going to see that that is going to be a fairly strong acid. Just by moving 0.5 units over right here, we've decreased the acidity of it because our anion here is not as stable as the fluoride ion because it was less electronegative. So it's less stable, meaning that we've gone from, this is the strongest, we've gone down in acidity just by moving over 1 atom on the electronegativity scale. And if we move over 1 more atom, it goes down again, such that we see it go from approximately, I think this is 1.7 to 16 to 24. And by the time we move over 1 more atom to the carbon here, this is all the way up to 50. Right here. So our acid strength is decreasing solely based on that drop in electronegativity, and that drop in electronegativity is its inability to stabilize that negative charge. Okay, so let's look at that in another way though. So the other way to do it is a large ion can cover that negative charge over a larger area or volume, and therefore that also makes it more stable. So that means the size of the atom depends more than the electronegativity of the atom on the system, because as you get a bigger and bigger volume, it becomes more and more stable. So how do we demonstrate that? Well, let's look down the column here. We've already, oh no. Okay, come on. Let's look down the column instead. We've already looked over this column here. Let's look down this column. So fluorine is the most electronegative atom, and chlorine is less electronegative. However, chlorine is much, much larger, okay? Which actually turns out that fluorine, which is at 1.7 here, chlorine is at minus, I think 7 right here. And that has everything to do with size, not electronegativity. Chlorine is almost twice as big, which means when we move to bromine, even though it's less electronegative, it should be more acidic, and it is. It's a -8. And iodine is the biggest of the SAT, and so we expect it to be the most acidic at -9. Okay, so And it all has to do with the chloride ion is nice and stable. It's spread out over a large area, but bromide is even happier. It's even a weaker conjugate base. It's happier because it's bigger and spreads that one negative electron over a bigger amount of area and volume. And the iodine's even larger, driving it to be the most acidic of the set. Okay, so we have to compare electronegativity versus size. And notice in the first row here, they're all about the same size when they form the anion. So all we're looking at is the effect of electronegativity. When we move down a row, down a column, we're looking at the effect of size. Okay? And for my last slide, I want to show you this one right here. Okay, so this is a good demonstration of the electronegativity versus size. So if we move one over, we've already looked at these. Oh, I was at one off. Okay. Water is about 15, going up to sulfur, which is twice as big as there. It goes to 7. It's more acidic. Selenium is even bigger. It's more acidic. And tellurium is the most acidic of that column. Those are all in the same group. The only difference is their size. So we're comparing, contrasting two electronegativity versus size. Okay, we're going to end there. I'm sorry, I ran a minute over, but we will continue there with some other things about the value, about things that the 3 other things that affect acidity. The numbers would be the pKa. Yes, those were all in pKa's, yes. Okay, I'm gonna go ahead and stop sharing and stop recording.